Hi everyone, I'm going to go over question number 17 from the chapter 14 bingo problems. So first off, I'll read the problem. It says, weighing astronauts. This procedure has been used to weigh astronauts in space. A 42.5 kilogram chair is attached to a spring and allowed to oscillate. When it is empty, the chair takes 1.3 seconds to make one complete vibration. But with an astronaut sitting in it with her feet off the floor, the chair takes 2.54 seconds for one cycle. What is the mass of the astronaut? So I've already written down the given information. So we know the mass of the chair, the period with just the chair, which is 1.3 seconds, and then the period of the chair with the astronaut in it, which is 2.54 seconds. So that's all the information we really need. The only equation that we'll need is one of our period equations. It's one of our chapter 14 equations. So it's T equals 2 pi times the square root of m over k. And this is the only equation we're going to need. We're going to use it twice, but this is it. So it's pretty straightforward. So first off, what we are going to want to do is we're going to want to find the spring constant. And so to do that, we just need to rearrange this equation to solve for that. And by the way, the period will just say C and the mass is just C. That way we can differentiate since there are multiple masses and multiple periods. So anyway, so we'll start out by squaring everything. And then what we'll end up with is K is going to equal 4 pi squared times the mass of the chair over T squared. Now that we have solved for the spring constant, we can just plug in the values that we know. So we know that K is going to equal 4 pi squared times the mass of the chair, which is 42.5 kilograms, over the period of the chair, which is going to be 1.3 seconds squared. When we do this, we'll throw it into our calculator, and our K value, so our spring constant, is going to equal 992.8. So now we know the spring constant of our system. But now what we need to do is we need to use that same equation again, but this time instead of using the period of the empty chair, we need to use the period of the chair with the astronaut in it. So we're going to say TCA this time is equal to 2 pi square root of the mass of, and that's the combined mass of the chair and the astronaut, over our spring constant. So like last time, we're going to have to rearrange the equation, but instead of solving for the spring constant, we need to solve for that combined mass. And so we'll start out the same way. We'll square both sides. And then, oh, that is not equals, that's multiplied. So now we just solve for this mass. So we'll end up with the mass is equal to t squared times k over 4 pi squared. And of course this period is that combined period. So now we can solve, since we've already found this spring constant. We only have one unknown variable, so we can just go ahead and solve this right here. So we know that our period is 2.54 seconds. That's squared. We know our k value, our spring constant, is 992.8. And then it's a really bad straight line, but you get the idea. And then 4 pi squared. We throw that in the calculator, and we end up getting that MCA equals 162.2 kilograms. So might be easy to think that that's our the mass we're looking for, but we need to remember that this is the mass of the combined mass of the chair and the astronaut. So I'm just going to rewrite it up here to get more room. So what we need to do is, we know that the total mass, which is here, minus the mass of the chair, is going to equal the mass of the astronaut. So we can write that out by saying like m sub a for mass of the astronaut equals mca minus mc. So mass of astronaut equals mass, basically total mass minus mass of the chair. So we know that our MA, or M sub A, equals 162.2 minus 42.5. And of course, this is all in kilograms. So we end up getting that M sub A, or the mass of the astronaut, is equal to 119.7 kilograms, or if you want to round it, it's about 120 kilograms. So that's our answer for this problem. I hope, as always, that you'll learn something. As a brief little review of what we did, we used our one of our equations for the period to solve for the spring constant, and when we did that, we were able to solve for the total mass, and then we were able to just use some simple addition, or I guess subtraction, to find the mass of the astronaut. So anyway, once again, thanks for watching. I'll see you in the next video.